Hi, everyone. My name is Duncan McGee. I'm a biomedical engineering student here at West Virginia University, and I'm going to be talking about 3D bioprinting and tissue engineering. So I'm going to talk about explaining kind of what 3D bioprinting is, some of the common strategies used in 3D bioprinting, as well as the bioinks used in it. Then I'm going to talk a little bit about some of the limitations as well as the advantages of 3D bioprinting and how it can be applied to tissue engineering, as well as some of the future applications and how it can be useful going forward. So first off, kind of what is 3D bioprinting? So 3D bioprinting in general is an additive manufacturing technique, and it's primarily used in tissue engineering. So far it's been used to develop many different types of tissue, from skin and bone to cardiac and muscle and liver tissues. And so it starts out by isolating cells from either a patient, an animal, or another source, which is then incorporated into a bioink, which contains the cells, biomolecules, and other biomaterials. This bioink is then used in different bioprinting methods, which can be inkjet, laser-assisted, vat polymerization, and extrusion-based, which I will talk about in more in detail later. And all of these allow for a 3D scaffold or structure to be printed, and this can be used for then implementation in patients possibly, or even in drug testing, or in the future, possibly entire organ transplants or reconstruction. So the first type of 3D bioprinting that was developed is inkjet bioprinting, and it's similar to 2D inkjet printing, which is found in common paper printers. And it uses the same concept and methodology. So you start with a tank of the bioink in this case, and it is passed through the printing head, and then a either thermal or piezoelectric actuator creates a vapor bubble which disrupts the flow and causes small droplets of bioink to form. And these bioink droplets are deposited onto a build plate and form a pattern, and this is built up layer by layer to form a 3D structure. So in general, 3D bioprinting is fast and cheap because it uses existing technology, and it has a high cell viability. So cells can survive very easily and then populate the scaffold. However, one of the drawbacks is the printing head can become clogged with viscous bioinks, in addition to using a high density cell density that can also clog the printing head. So far, using this technology, alginate and collagen have been used to bioprint blood vessels, bone, and cartilage, along with other different bioinks and tissue types. Another type of 3D bioprinting is laser-assisted bioprinting. So similarly to inkjet bioprinting, it's used to form small droplets of bioink, which is deposited onto a build plate and then used to create a 3D structure in layers. So this technology works differently from inkjet, in which a laser is used to strike an absorbing layer which evaporates and causes the bioink droplets and the bioink in this case consists of a hydrogel and the cells, and it causes these droplets to form, which then fall into the plate and form the structure. This technique allows for high cell viability and a very high resolution, in addition to being able to print viscous bioinks, which is different from the inkjet printing. However, due to the use of the laser and this technology, it makes this method pretty expensive and hard to implement. And the effects of the laser exposure on cells when bioprinting is not fully studied and understood yet. So one of the other techniques used in 3D bioprinting is vat polymerization. So both these rely on the idea that you have a vat of bioink, and it can be selectively polymerized using ultraviolet radiation. So two of the vat polymerization bioprinting techniques are stereolithography, which is known as SLA, and digital light processing, which is DLP. And both of these use a UV source, which is then used to polymerize a photopolymer bioink. And in these, for SLA, it takes a UV source and focuses it down into a point, which is used to then cross-link the bioink in certain positions and form a pattern, which is then built up layer by layer, while the DLP uses projection lenses to project an image, which then polymerizes the photopolymer. This technique is useful because it has a high resolution, but it does require specific photosensitive polymers, and it does contain cytotoxic photoinitiators, which can inhibit the use for bioprinting. Another drawback is that both SLA and GLP are fairly expensive to implement and use. One of the more common methods that has been used recently is extrusion-based bioprinting, mainly because it's easy to implement and fairly cheap and accessible. It involves a pneumatic or mechanical force. Typically, a plunger or a screw is used to apply the mechanical force, or air pressure is used for the pneumatic. It works by extruding bioink through a nozzle, and it comes out as cylindrical lines as opposed to droplets like the inkjet or laser-assisted bioprinting. This technique does have low cell viability because the pressure that builds up can lead to mechanical stress and damage the cells. But it, like I said before, it can use many different bioinks and is very simple and easy to implement. In general, with all of 3D bioprinting, one of the difficulties is creating a tissue that is able to support itself, because many of the bioinks don't have the certain mechanical properties that are needed to construct tissue while also maintaining their own structural integrity and not falling apart. So one of the methods that has been developed recently at Carnegie Mellon is known as FRESH, and it looks to mitigate these problems and address the mechanical properties of the bioink. So in this technique, FRESH bioprinting, it stands for freeform reversible embedding of suspended hydrogels, and it was developed to allow these soft bioinks to be printed. So typically, if you tried printing with a soft bioink, it would just kind of fall apart due to gravity. But a micro particle gelatin support bath is used in this case. And how it works is it typically uses extrusion-based bioprinting, where the nozzle deposits the bioink into the gelatin support bath, and the gelatin support bath holds the bioink until it can be polymerized and cross-linked. So in this paper that I read and studied, they used sodium alginate as the bioink and did not incorporate any cells into it. At this point, it's just used to create a full-size heart model. So they used CT scans to create a 3D model of the heart, created code that would then tell the 3D printer how to print this full-size model. And the alginate bioink was cross-linked using calcium chloride, which was incorporated into the gelatin support bath. So this FRESH technique allows for the support bath to incorporate multiple different cross-linking techniques. So you can use the divalent cations like calcium, which can be used to cross-link alginate, or you can use pH change or UV radiation as well to cross-link the bioinks. So for this case, they successfully printed a full-sized heart model using alginate and calcium as the cross-linking agent. So for different types of bioinks that are used, I kind of mentioned this before, they have to meet certain biological, chemical, and mechanical properties so that they can replicate tissue. So this can be done using either natural or synthetic polymers. And typically these polymers are capable of forming hydrogels. And then that in combination with the seed cells allows them to replicate tissue. Some of the natural polymers that are favored are polysaccharides and proteins. So this includes polysaccharides like alginate and agarose, as well as collagen and gelatin, which are proteins. And the natural polymers are used more commonly and are generally favored because they're biocompatible, as well as having similar structural properties to that of tissue found in individuals. Synthetic polymers as well are used. Some of them that are used are polyethylene glycol and pluronic, and they're used because they're able to form hydrogels, and some of them do have low toxicity as well. So these bioinks have different cross-linking methods and strategies. So the polysaccharide alginate can be cross-linked by calcium ions to form a hydrogel, while gelatin methacrylate, also known as GELMA, can be cross-linked using UV radiation. So there are a lot of different strategies using different bioinks and combinations of natural and synthetic polymers or proteins and polysaccharides, where in general they all follow the same idea, where some type of cell is incorporated with a polymer and a cross-linking agent, and it forms a bioink hydrogel. So for 3D bioprinting, Some of the major limitations is the mechanical properties of Bioinks and their cross-linking strategies. So as I was just talking about the last slide, the mechanical properties, they have to mimic the tissue that you're trying to replicate. So the structure is directly related to how it will function in the body, and certain bioinks are better at replicating different tissues. For specific types of bioprinting that have limitations, extrusion-based and laser-assisted have low or unknown effects on cell viability, like the mechanical stress caused in extrusion-based printing can damage the cells, as well as the unknown effects of lasers on cells in laser-assisted bioprinting. For the vat polymerization techniques used in bioprinting, SLA and DLP, they both utilize UV radiation, which limits it in two ways. One is through the material selection, because it has to incorporate a photosensitive polymer as well as photoinitiators, in addition to the UV radiation itself having an effect on the cells, as you can see, like how the sun causes skin cancer in humans. Overall, some of the limitations have been developing with organs has been developing complex tissue models that incorporates different types of tissue and the vasculature, in addition to bioprinting in general just being fairly expensive to implement because of all the high cost of all the different components. However, as there are many limitations to it going in the future from replicating organs and tissue, it still provides multiple techniques that are capable of recreating specific types of tissue. And 3D bioprinting has been very useful in recent years at creating models for specific tissues. So like extrusion and inkjet based bioprinting are relatively cheap to implement and have been more common, while like laser assisted SLA and DLP, the vat polymerization techniques, they offer really high resolution, so you can make very detailed tissue. Extrusion based biometering, like I said, is easy to implement, and it can support a wide variety of bioinks and cross-linking techniques. So 3D bioprinting in the future for modeling tissue or replicating organs can kind of personalize the tissue scaffold in two ways. One can be in size, so each individual has different sizes of organs. So in the future, if you wanted to do organ implantation and transplantation, you could scale the model to different sizes for each patient. In addition, another personalization technique would be to use an individual's own seed cells to populate the bioink. And this would help with rejection of organs and limit the amount of disease transmission. So this kind of goes into the applications of 3D bioprinting. So like 3D bioprinting has been used in tissue engineering already to generate many different types of tissue, one of which has been cardiac tissue. So in one study, they made a fibrin-based composite bioink and populated it with cardiomyocytes from rat hearts. And they were able to successfully print cardiac tissue. And then they were able to study it as a model and compare it to how cardiac tissue typically works in a human. Another study looked at an aortic valve conduit. And this is typically used in surgery to help replace the aortic valve when it's been damaged. And in this study, as shown in figure 8, you can see they have a 3D model of the aortic valve and then the bioprinted valve conduit. And they used an alginate gelatin bioink containing valve interstitial cells. One of the limitations with bioprinting and reconstructing organs has been creating the vascularization in that. And so one study looked at using sacrificial agarose to create microchannels in JELMA for tissue engineering in the future. Kind of in a related but slightly different application of bioprinting is, instead of just tissue engineering for implementation into humans, would be more drug testing and disease testing, where it can be used to create tissue models and possibly replace animal testing in the future. So like I say, in the future, it's currently not possible to create a fully functioning bioprinted organ, but it might be going into the future once more research has been conducted and more time has been committed to the study of bioprinting. So like organs are needed worldwide, and it's a problem for people to find organs off the organ donor list. So 3D bioprinting might be able to provide a solution to this. And as I mentioned before, it can personalize organs to an individual by using their own cells and reduce the risk of disease transmission or organ rejection. In addition to possibly recreating tissue models, 3D printed tissues, and organs, 3D bioprinting can also have other future applications that we haven't discovered yet. One of which has been hypothesized is regenerative therapies, where bioprinted tissue can help replace and repair damaged and dysfunctional tissue. So kind of in general, 3D bioprinting has just kind of been a new technology that's been developed, and hopefully in the future with tissue engineering, it can be used to create more accurate models for disease and drug testing, as well as even recreating organs. And here are some of the references that I used for this presentation.